So when graphing, first to review everything that we've done so far as how to use calculus for graphing. We still use some things from previous years, like if we can find x-intercepts and y-intercepts without our calculator, we're going to do that. And we'd probably do that first. For example, on this one, if you plug in 0 for x, you get 0 for y, that will be quite easily your y-intercept and also going to be an x-intercept. If I wanted to find an x-intercept, I would plug in 0 for y and try to solve this. And in this case, you can factor out an x cubed, leaving you with x cubed times x minus 4. So you would get x equals 0 and x equals 4. We already found 0, 0. But we now know that our x-intercept is 4, 0. So that's some stuff from previously. Then the process of using your derivatives, we have our first derivative and our second derivative. Obviously, we're going to do the first derivative first. That number line will tell where a graph is increasing and decreasing. And that number line will also tell us our maximums and minimums. Then we're going to do our second derivative, and the number line for the second derivative is going to tell us where things are concave up and concave down, and it will find our inflection points. And once you have those two number lines and your maximums and minimums increasing, decreasing, your inflection points with concave up, concave down, it becomes really easy to graph. So if we start off with our first derivative, you'd get 4x cubed minus 12x squared. We set our first derivative equal to 0 to find our critical points. In this case, I could see a common factor of 4x squared to pull out, leaving me with x minus 3. And so we get x equals 0 and x equals 3 as critical points. Those critical points, we put on a number line for a derivative, 0 first, then 3, and we check values in our derivative to find out where it's positive and where it's negative. So for example, if I choose something less than 0, I hope you can see that this 4x squared part would always be positive. And if I plug something less than 0, like negative 1, this section will be negative, and so our graph will be decreasing as it goes to 0. Secondly, if I plug something between 0 and 3, 4x squared is still positive, x minus 3 is still negative. And so this is an interesting graph because we have two sections negative in a row. That does tell us something about 0. 0 is not a minimum. It's not a maximum. It will be a stationary point of inflection. So there's going to be, it's going to flatten out but keep going down. But when I plug in something larger than 3, this section becomes positive. This will increase. So we know that 0, 0 is a stationary point of inflection, and that at 3, comma something, that is going to be a local min. And we can see from our sign diagram that it will be a local minimum. Two things needed for showing something's a minimum or a maximum using the first derivative test. One, the first derivative is equal to 0. We showed that. And then two, if it changes from decreasing to increasing, that would make it a minimum. If I want to find the y-coordinate of that minimum, I have to go to my original equation and plug in 3. 3 to the 4 is 81 minus 27 times 4, 108. 81 minus 108, negative 27. That's our local limit. Second derivative. Find our second derivative. It's going to be 12x squared minus 24x. Set it equal to 0. Factor out a common factor of 12x. And we get x equals 0 and x equals 2. We make our number line with those points for our second derivative with 0 and 2. Again, I'll use the factor part. If I plug in something less than 0, this is negative, this is negative. Negative times a negative, our second derivative will be positive, and your number line for your second derivative tells you this is concave up. If I plug something in between 0 and 2, this is positive. That factor is still negative. Positive times a negative. This part will be concave down. And finally, plugging in something bigger than 2, both of these factors are positive. Back to concave up. So we know that both 0, 0, and we knew that one already, but now 2 comma something is also an inflection point. And to find out what that coordinate is, again, anytime you're finding an actual coordinate on the graph, you have to plug that back into the original equation. Very tempting to plug it into a different equation. You have so many equations that you plug things into, so that's one of the difficulties in curve sketching, is just keeping that under control. So 2 to the 4 is 16 minus 32, negative 60. And this is curve sketching, and we can draw something very accurate as a result. And, oh, I'm excited about this one. I get excited about lots of graphs, but this one has some good stuff from grade 12 to remind us of things we saw in grade 12 and be able to graph it really quite accurately. So, for example, we have 0, 0 and 4, 0 as x-intercepts. We've got 3, negative 27 and 2, negative 16. So maybe I will go whatever scale you pick, you have to make sure that that scale seems accurate. Have you guys seen the Ivy graph paper? Have I ever showed you the Ivy graph paper? I'll show it to you later. I'll find something. It's intense. Because regular graph paper just has grids, right? They make their grids a little bit bigger and split each of their grid sections into 10 by 10 mini grids. So you've got little boxes all over the place. But for some really high-end scale diagram stuff, it is quite nice. You ever been to the Bannatyne playground? There's a maze. I designed that maze on Ivy graph. It was very mathematically, it was very fun because Home Depot came to build that maze, and they built that maze in like under an hour based on the measurements on Ivy graph. It's great. I hope you never get one. You can just look around, step over it, get stuff. Okay. Whew. Okay. 3, negative 27, so I can label that point. That's going to be a local min. Oh, I like blue. Let's change it. And we've got also 2, negative 16, that's going to be about here. So here we've got 3, negative 27. Here we've got 2, negative 16. And what do we have to graph this? We know that it needs to be coming down. So it's going to start up here because it's coming down. It needs to be on the left side of 0, concave up. So I can show concave up like that. I often like to start with my inflection points because I find if I start with my pen or pencil on an inflection point, I'm able to make the concave up or concave down easier. Okay? From 0 to 2, it needs to be concave down. So if I was showing that, I could do like that. And from 2 on, it's concave up with 3, negative 27 at a minimum. And we have a very accurate graph. And the reason I got excited about this graph is because if you think back to grade 12, do you remember graphing an x to the 4 in grade 12 pre-calculus? What you would have learned is you would have said, oh, it's a positive x to the 4 graph. So you'd have learned its end behavior was like a parabola. It has to end up here and up here. That matches up with what calculus told us. Then you would have found your x-intercepts of 0 and 4. And do you remember in grade 12, they said, oh, this 0 has a multiplicity of 3 because it happened 3 times. And you learned when something had a multiplicity of 3, there was a bend in the graph. That bend is accounting for a stationary point of inflection. Now, by showing concave up and concave down, you make the bend naturally. You can't not make the bend if you draw your concave up and concave down. So you don't have to remember the bend anymore because it just happens naturally. Okay? In grade 12 pre-calculus, though, you had no idea how low it went. You just estimated that. You also had no idea where it changed back from concave down to concave up. But those points, when you draw a smooth curve through that, it's actually amazing how accurate every other point is in between that we draw. Probably the only thing I'd be like, I don't know how accurate this part is. But the rest of this, by drawing it smooth, is going to be actually fairly accurate. So it's just kind of neat to see how what we learned in grade 12 pre-calculus had some stuff, but now calculus just makes it all make sense. And how some of the things like multiplicity and end behavior you don't even need anymore because the calculus fills that in. Whew. 2x e to the x. Great. Just so excited to have an e in this graph. So let's see what can we do with this and what kind of analysis can we have. First of all, you could easily find your y-intercept. If you plug in 0 for x, you get 0 for y. So we know that we're going to have an x-intercept and a y-intercept of 0 and 0. As far as solving for x-intercepts, technically, I'm going to put the e to the x in brackets here. It's the same thing as multiplying. But if I want to make y equal to 0, I can split it here. Obviously, this part is 0 when x is 0. But I want you to, one of the skills that they want you to have in calculus is the ability to solve things using not only algebra, but an understanding of graphs. Like, I know what the e to the x graph looks like. It is, if I graphed y equals e to the x, it had an asymptote here, it's exponential, and was increasing like this, it would have the point 0.5 0, 1, 1, e, and all exponential graphs look like that. The important thing that the graph tells us is it never equals 0. By having the graph, we can answer that section that is never 0 easily. Algebraically, you'd be looking at that and going, okay, I have to use my logarithms and use all my log laws and solve, and you'd end up finding something that didn't work, and then you feel like, did I make a mistake? Your algebra sometimes makes you get lost. And so all of that work we did graphing, graphs sometimes help us more than algebra. Algebra sometimes help us more than graphs. Having all of them available to you gives you the best opportunity to quickly answer a question. So we have only 0, 0 as a point so far. That's our only x-intercept. That is our only y-intercept. We'd have a problem if we had more than one y-intercept. It wouldn't be a function. But you can have more than one x-intercept. In this case, we do not. Now, first derivative. You should write out the derivative yourself. I know how to do it. See how strong. You had 2 days off on the weekend. How good did your derivative stay? Did you see it as a product rule? No. See, this is good. This is why it's good for me to say first, try it. Because if you're making those mistakes when you try it right now, even if I do it right, the next time you have to do it on your own, you will still make the same mistake. It's a weird phenomenon that I've noticed in teaching. It doesn't matter how many times you see it right. If you're scheduled to do it wrong the next time, you're still going to do it wrong the next time. So having that opportunity to try it in class, and be like, oh, I forgot it was product rule. Product rule, this is where the product is, right? There's our dot. So we keep the first one the same. I kept the 2x the same. Derivative of the second one, which is still e to the x. And then I kept the e to the x the same, and derivative of the first one was 2. Which, if I set this equal to 0, I can factor out a common factor of e to the x. Technically, I could factor out a 2 e to the x. That's even better, leaving me with just x plus 1. When is this equal to 0? When x is equal to -1. And this one here, again, it comes in handy that we have that graph. That part's never equal to 0. So when we draw our number line, we get -1. Now, the last two examples haven't had a situation that sometimes comes up. Not only do we put our answers to where the derivative is equal to 0 on this number line, do you remember what other values we have to put on that number line if they exist? Yeah, any non-permissible values. Now, we didn't have non-permissible values in the last two examples, but it's good to remind ourselves of that if that comes up, we would put that on as well. So this is my first derivative. I'm going to plug things in. Okay? Also, from the graph, how helpful is that graph to tell me 2 to e to the x is always above the x-axis? It's always positive. So now when I plug something in less than -1, I have a positive times a negative. I know that it's decreasing here and then increasing after. So I know that -1 comma something is a local minimum. How do I find out where that local minimum is? I plug it back into my original equation. -2 e to the negative 1 would be move that e to the bottom. Negative 2 over e. Beautiful number. Okay. Next, our second derivative. For our second derivative here, we're going to have to take our derivative of our first derivative. I could either, wow, notation-wise, I shouldn't do that. I was using y's. Should stick with the same notation all the way through. So y double prime, second derivative. I could either use the factored form or the original. Do you have a preference? You want to use the factored form? If you use the factored form, do you see that you have a product rule again? So we would keep one the same. Let's say I keep this one the same. Derivative of the second one would be 1. Then I keep the second one the same. Derivative of the first one would be 2e to the x. And just like previous ones, I can factor out a common factor of 2e to the x, leaving me with 1 plus x plus 1, which is, I set equal to 0. Then again, this is never 0. This is always positive. I noticed I did this before too. I switched notation on my number line. I guess I'm okay with it. I always was using f prime on the number line. Kind of feeling like I'm okay with it. I'm going to go back this way. Negative 2. If I plug in something less than negative 2 into this will be negative. Concave down. And positive. Concave up. Okay? And a negative 2. If I want to find that coordinate, I've got to plug it into the original. The original equation will give me negative 4 e to the minus 2, which would be e squared on the bottom. Now, we can graph. We have all the information here to graph, and I'm excited about this graph. I'm excited about everything. But this is not something you could have graphed with anything with grade 12 pre-calculus. And even though we've done calculus, it's still not the prettiest as far as numbers go. Negative 2 over e. Just set a scale here. Negative 2 over e, can you see that's just a little bit less than negative 1? Because e is 2.7. So I'm going to label that point negative 1. Negative 2 over e. And then I also have to label negative 2, negative 4 over e squared. Negative 4 over e squared is that, we should actually use a calculator to see some of these things, but it's going to be fun. Okay. Now, to quickly graph this, it needs to be decreasing, then increasing. And it needs to be concave down and concave up. So I'm going to start on my inflection point. There's concave up. Now, this part needs to be concave down and also needs to be decreasing, plus we no longer have any x-intercepts. In other words, there's most likely an asymptote at y equals 0. If you think about this, as you plug in a very large negative number, can you see that e to the x goes to 0? And 2 to the x goes to a negative infinity. So that we have to do some upper level calculus to make sure we know that there's an asymptote. And double check it on our graphing calculators.